So welcome to the next class. Today is one day after 16th August, an eventful day, right? We were looking at a plant-wide control design procedure which is attributed to Lieben. They were the first ones to sort of systematize what needs to be done, and the basic idea is do the most important thing first. What is most important is stabilization, particularly if you got exothermic reactions. You need to establish an energy management system first. You need to make sure that whatever heat is being released by the reaction is effectively removed, right, so that there is no possibility of a thermal runaway. That's all that this means. And what I was trying to tell you last time was that reaction systems and corresponding heat removal systems are designed, and that design itself tells you the best way of removing heat in terms of control, right. That is what I was trying to tell you last time. Then you fix production, and before controlling inventories you control everything else that is more important. So, product quality is going to be more important. What else? Any safety considerations, for example, flammability limits, process operation should never wander into the flammable region, right, that is important. And any environmental concerns. So, these variables will have to be tightly controlled. In order to control them tightly, you need handles that are close by, right. If the handle goes far away, then there is a large lag, and if there is a large lag, the control cannot be as tight, right. So, these things need to be done when you have the maximum availability of valves. So, you have taken some valves away for reactor stabilization, you have taken one valve away for throughput manipulation. Then your next in terms of priority concerns are product quality, safety and environmental. You form loops that will give you tight control, right. That means you have to use close by handles, right. After that you will still be left with sufficient number of valves to regulate inventories, okay. That essentially fixes your control system. Nevertheless, the plant wide control system, nevertheless, because some mistakes can happen in terms of putting in place a control system that does not respect overall component inventory balance for at least one component, or sometimes maybe even total material balance. It is important to check that whatever control system you have put in place, it respects material balance. Everything that is coming into the process either gets reacted away or finds a way out, right. Double check that. So, this is step number 7 is essentially double checking this, that a mistake has not been made, because if a mistake has been made, that control system is doomed. Guaranteed something will build up or something will deplete, and then you will have to take a shutdown, okay, guaranteed. So, it is important to stress point number 7. Usually after you have done all of the above, okay, you have stabilized the heat, you have stabilized the exothermic reactor, you have chosen a throughput manipulator, you have put in place loops for product quality control, safety concerns, environmental concerns, you have put in place loops for controlling levels and pressures, okay, and component inventories if necessary. You will still have degrees of freedom that are left. Those degrees of freedom can be used to tighten up the control on a local unit operation, okay. For example, in a distillation column, you may say that, okay, I am going to keep the reflux rate fixed, but to improve the energy efficiency of that column, you may say that, okay, instead of controlling one tray temperature, I will control 2 tray temperatures, and now I am going to move my reflux rate in to maintain, for example, a rectifying tray temperature. What that does is it actually improves the energy efficiency of your process, okay. You consume less steam for the same production, okay. Similarly, you can think of whatever valves are left, whatever degrees of freedom are left, they can be used to improve control of local unit. In a, for example, in a furnace, in order to ensure that the combustion is near complete, you will always be monitoring the stack gas composition and then adjusting the fuel to air ratio to ensure combustion is near complete, right. That is to basically have efficient furnace operation. Whatever fuel you are putting in which is precious must get fully combusted, right. So, there will always be degrees of freedom that can be adjusted for more efficient unit operation control. Do that, okay, and there are books that are available that will help you do that. I mean, that's pretty reasonably well established. Even after doing that, you will usually still have a few degrees of freedom that are left. Those can be used to either improved for either better dynamic controllability, smoother operation, or for improving economics, for example, yields, process yield, suppression of side reaction, etc., etc. Okay. So, this is the 9-step procedure. I hope the hierarchy and why what is being done first and what is being done next is organized the way it has been organized. Inventory control is usually, tight inventory control is usually not desired. It is not important to have tight inventory control. In fact, if you have put in place a reflux drum, or let us say a surge drum, and you are doing perfect level control, what does that mean? If flow in changes, flow out changes immediately. That is like incompressible flow. Why the hell did you put in place that drum to begin with? You put in place that drum to dampen out flow variability, but then your level control is extremely tight. Flow variability is not getting dampened out, right? Flow increases, level control is perfect, flow out also increases simultaneously. Where is the dampening of flow variability, right? Why the hell did you put in place that surge drum to begin with? You might as well have put a straight pipe. Yeah. So, the whole point is that these surge inventories are actually shock absorbers, like in a car. You want that shock absorber to move, you want it to fluctuate within limits, of course, so that the shock absorber does not damage the shock absorber itself. So, it should not happen that a tank level goes down below 20% and an alarm start going off, or that a tank level should go beyond 80% and again alarm start going off. As long as the variability is allowed to be in that band, you are absorbing shocks. Yeah. And just to give you a perspective on this, I think it is important to, this is a very simple example, but it sort of captures what is being said. Let us say I have got a heat exchanger, let us say there is a process stream that goes through the tubes, and let us say you are heating it using steam. Okay. So, there is steam going in. Okay. You have got a temperature indicator here, and what this temperature indicator is doing is showing you what the temperature of the process stream is. Let us say it is important that this temperature should be held flat, should be held constant. Maybe this is something that is going into a reactor, and it is important to not let that temperature fluctuate. Okay. If that is the case, and let us say you are running this guy like this, there is a flow controller of steam and this set point is set by the operator. Okay. Now, let us say the flow through the heat exchanger, maybe I should also show some. So, these are tubes. So, this is a heat exchanger, process stream is flowing through the tubes, steam is on the shell side heating it up. Okay. Now, because the temperature of whatever is the process stream that is going in, T in, because T in varies, because F in varies, and also maybe because the pressure of the steam varies. Okay. What will you see on the temperature side, on the exit side, on the process stream outside? What will happen to the temperature? It is going to fluctuate, right? Because of all these reasons, you are holding the steam constant, because the flow rate through the heat exchanger is changing, because the temperature of the feed stream is changing, and steam is held constant. You are going to see that the temperature is varying. Now, for whatever reason you decide that, look, this variability in the temperature is not acceptable, because for example, it is feeding a reactor or maybe a distillation column or whatever. Okay. That being the case, you say, well, what I am going to do now is put in place a control system, a cascade a control system. What that does is takes the temperature reading, compares it with a set point, and then adjusts the steam flow. Okay, let us say this is what you are doing. Now what you, so in the previous case, when the green, what is in green was not there, steam flow was fixed. This is steam flow, okay, F steam, and this is T out. Under open loop operation, what you have is the steam flow rate is fixed and process temperature is changing. If you close the loop, if you put in place that green loop, okay, now what is happening, and if it is tuned well, now temperature will be close to the set point. What you will have is temperature is, it will show some variability, but not too much, okay. And what is happening to the steam? To hold the temperature constant, the steam is actually going all over the place, yes or no? I mean, again it is very simple minded. What has the feedback control action done? It has essentially transformed process variability from, exactly, the feedback action has transformed variability from here to here. That is what feedback action is doing, right. So, a control system is nothing but an agent for transforming process variability. Now, you have to decide where do I want the variability to go. In a plant wide control context, if I am controlling level here by adjusting downstream flow, and let us say downstream there is a distillation column, in order to hold the reactor level constant, I am disturbing the separation section, the distillation column, right. I could, for example, hold the flow to the distillation column constant and control the level this way, yes or no, and now the variability is being transformed away from the distillation column. So, now the whole idea behind plant wide control system design is, where is variability acceptable and where is variability not acceptable. Obvious place where variability is always acceptable is levels, except maybe for a reactor where you want to operate the reactor at maximum level because that maximizes conversion. But any surge drum, level variability is acceptable, okay. If you want to systematize this further, any constraints that are becoming active, okay, for example, you want to run this column at flooding because that maximizes the recycle rate, and maximizing the recycle rate creates maximum excess inside the reactor, and that suppresses the side reaction, okay. So, you got a very good reason to maximize the boil up, okay. If you are not able to maximize the boil up, that reduces your yield, and that is a what should I say, an economic penalty for you, right. In that case, I want really tight control of the boil up too, right. So, I do not want variability going towards the boil up or towards that column which I want to operate close to flooding. I want variability to go away from there. Do you see what I am saying? So, the whole idea is, which way should I transform the variability? You see, the moment I put in that loop in there, I am essentially saying transform variability from here to here. That is a structural decision. The moment you put in a loop, you have essentially decided I want to take variability from here and I am going to transform it there. That came because you structured a loop. When you are designing an overall plant wide control system, those structural decisions are in your hand, right, and those structural decisions now have to be taken so that variability is transformed away from all, for example, active constraints. Do you see what I am saying? That is the basic idea, okay. And if you consider this perspective, you will find that, look, this actually makes sense. Energy management system, if something is going to go unstable, you want to do it the best possible way, use the closest possible handle. Product quality will always be an active constraint variable. Safety concern will you want to operate close to flammability limit but not in the flammability region, right, tight control. How close can you operate, that will be determined by how tight you can control it. Same thing with environmental, zero discharge or minimum discharge, right? You want to control these things tightly. So put in place loops that help you do that. When you put in place the loops, variability in these variables gets transformed to whatever you are manipulating. Yes or no? Okay. Control inventories comes later, and you don't want to control them too tightly, because if you try to control them too tightly, just like I gave you the example of a simple tank, you put in place a tank to dampen out flow variability, and if you control level tightly, you essentially get no damping, right? So this whole idea of what are my active constraints, how do I structure my control system, my plant wide control system, so that the variability is getting transformed away from things that need to be active. Okay, does that make sense or no? Once we have converged on this, I think we can now proceed a little further. Let me just take an example, and I would like to refine this a little further. Okay, the basic idea here is control what is important first when you got maximum number of degrees of freedom in your hands. The whole key is deciding what is important and what is not, right? So these guys have decided quality is going to be important, safety is going to be important, environmental concerns are going to be important. Control them tightly first, then we will control inventories, right? Now sometimes, not sometimes, all the time, when you do an economic optimization, you will find that multiple constraints are active. I just gave you an example, reactor temperature max, what is it, reactor level max, right? Column this in flooding condition, column that in flooding condition, etc., etc., right? These do not come in product quality or safety, these are coming from economic reasons. So I can alter this procedure by saying plus economic active constraints. Yes or no? You see, because something is some constraint must be active, because it gives you economic optimality, because it maximizes your operating revenue, or it maximizes yield, or it minimizes your energy consumption. You want to control that too tightly, yeah? Okay. So I am just going to alter, the philosophy is the same. I am just going to say that if I can optimize my flow sheet subject to process constraints, and that optimizer is telling me that in addition to product quality, safety and environmental concerns, this column should be flooded, that column should be flooded, this level should be max, that level, that temperature should be max. Well, those things too need to be controlled tightly. Yes or no? All right. Well, if those things need to be controlled tightly, well, I might as well do it early, rather than before the inventory control system has been put in place, because tight control of inventories is, well, tight control is not desirable. As long as it is in a band, it is okay, right? So I am going to do, so this is a slight modification, philosophy is the same. Now let us talk about examples, same examples that we are familiar with. What was the example that we are most familiar with? A plus B goes to C, C plus B goes to D, and C is your product, D is your byproduct, A, B recycle. Okay, so let us do that. This is your CSTR, exothermic, cooled, A comes in, maybe B comes in. You put this into a, well, I will put it into a stripper. That is done so that all degrees of freedom get exhausted. This is a stripper, okay. The vapor is condensed, condensate is collected in a drum, and we are operating essentially at zero reflux. Whatever is the condensate, it is sent, this is AB recycle, okay. Bottoms is essentially C and D, this is sent to a product column, where you take out light C up the top as the main product, byproduct D is taken down the bottom, and this is essentially AB recycle. This is A, maybe this is B, and if I start putting in valves, I've got a valve here, what's the degrees of freedom, steady state operating degrees of freedom of this process? Step number 1. Control objectives, of course, well, I'll tell you the control objectives too. Step 1, control objectives. Product quality, okay. What else? How about byproduct quality, the bottom stream? Let us say product quality has to be 99.9% mole percent pure, okay. Let us just say this is what I sell in the market, okay. How many degrees of freedom? First of all, count them. 2 for the fresh feeds, 2 for the CSTR, 1 for the stripper, and 2 for the column. How many? Kitne? 2, 3, 4, 5, 6, 7. Yeah, 7. Steady state operating degrees of freedom is how much? 7. How many valves? Better question. How many independent control valves? Just count whatever I have drawn. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Steady state degrees of freedom is 7. Number of valves is 13. You subtract the 2, 6 extra valves, right? These 6 extra valves are for what? Inventory control, right? Okay. Now, if my steady state optimizer says that, look, okay, this is a point that needs to be understood. I have got 7 steady state degrees of freedom. That means when I am optimizing some objective function, which what is the objective function? Let us say I want to maximize operating revenue. Okay, what is operating revenue? Product rate times product price minus raw material rate times raw material price minus energy cost. That's the revenue that the plant generates, right? I want to maximize this. Usually what will happen is that the product price is what is making the money. Energy is much cheaper than raw material or product price. So therefore what happens is maximizing revenue actually corresponds to maximizing production, particularly if you can assume that there is sufficient demand. You are the only guy who can make that product, so you there are no competitors because you got the patent, right? So maximize production, sufficient market, sufficient this, no matter what you produce, it is not going to affect the price, you know, fine, okay, fine. So then maximizing production is what you want to do, okay. Another mode of operation, this is called, you know, this is one mode where you want to maximize production or maximize revenue, or let us call this mode 2. There is another mode of operation where what is the feed to be processed is given to you, or how much product is to be made is given to you. Product rate is given, make 100 kilomoles per hour of product C, which is 99.9% pure, or 150 kilomoles per hour because market demand is increasing, okay. That we will call mode 1. So mode 1 is essentially given production. Mode 2 is what? Max production, max achievable production, max production, okay. Yes or no? Now let us take mode 1, okay. In mode 1, if I want to operate this process economically from a steady state point of view, that means I am considering my 7 degrees of freedom. How should they be adjusted so that my revenue is maximum for a given feed rate, for a given A feed rate, for example, okay. Reaction stoichiometry is A plus B goes to C, C plus B goes to D, C is desirable, D is undesirable, okay. So how will I suppress the D production rate inside the reactor? I want to maximize C, minimize D, right? Because any D I make consumes B, also consumes C. So any D that gets made consumes 1 mole of A and 2 moles of B, yes or no, and I don't make any money on it. I am paying money for those many moles of A and B, right, but I don't make any money on that D. So obviously I need to do what? I need to minimize the D formation or the D production rate and maximize the C production rate. Basically I need to maximize the yield. Economic operation will typically correspond to, for example, maximum yield, yes or no, maximum yield to desirable product. How do I maximize the yield? Kinetics will be such that D, activation energy of D is more than activation energy of C, which is why C is the main reaction, D is the side reaction. Because the activation energy is more and both reactions are irreversible, you change the temperature, percentage change in D formation will be more than percentage change in C formation, your yield will go down, yes or no. I think we discussed that some time ago. Yeah, okay. So once you have understood that, tell me how the hell do I suppress the side reaction as a chemical engineer? You have to operate the reactor in excess A. Yeah, let me also tell you, energy is much cheaper than product or raw material. Okay, so how do I, basically minimizing D corresponds to maximizing A inside the reactor, the excess of A inside the reactor. How do I achieve that? Okay, so how do I maximize the recycle rate? You will have to essentially operate the stripper at flooding condition, at maximum boil up. So basically I have got 7 degrees of freedom. Of those 7, fresh A rate is given to me. I am told that process 100 kilomoles per hour of A. Alternatively, C production rate may be given to me. Basically 1 degree of freedom is gone. It is set by throughput. Okay, that is gone. So out of 7, 6 remain. Then maximizing yield requires boil up in the stripper should be maximum. Yeah. What about reactor level? It should be maximum because it minimizes the, you see what will happen is, if I increase the level, boil up will go down because unreacted amount that is coming out is less, higher residence time, more conversion, less unreacted material to be sent up. What that means is I can increase the amount of boil up back to maximum, increase the recycle rate, and then I will get further suppression of the side reaction. So maximizing the level minimizes the boil up or reduces the boil up, which allows me to increase the boil up so that recycle rate further increases. So if I was able to operate at 50% level at a recycle rate of X, at 100% level I will be able, or at 80% level I will be able to operate at a recycle rate which is X plus something. That extra recycle rate that I am getting will help me further suppress the side reaction, yes or no. This is a qualitative argument. Okay. So I should also be operating the reactor at max level. Yeah, I want to produce 99.9% pure. Okay, what that means is I have got only 0.1% impurity in the C stream. Okay, what are the impurities in the top stream? D, that's it. B and D. Any B that leaks out is going to go up the top, and D is going to go up the top. Okay. Now let us say that I give you something which that C is much lighter than D, so the separation is easy. Okay, separation is easy. The energy consumption in the reboiler here in the second column is essentially the energy it takes to send C up the top. D being heavy will go down, D being very heavy will go down naturally. Okay, there is no energy penalty for D going down. Okay, because D is the heavy byproduct. Alright. So how should I manage it? Dimag lagao. Put your brains. Exactly. You see, D will anyway be a small stream. Okay, because you are running the reactor in excess, in a large excess. D will, so for example, let us say C is 95 kilomoles an hour, D may be 1 or 2 kilomoles an hour. Okay, I want to make sure that whatever C I am producing, it goes up the top, I do not lose it down the bottoms. Okay. What that means is I would like to, for example, but the separation is easy, so it does not make sense to, you see what can happen is, because the separation is easy and I put the boil up here at max, then what will happen is D will start going up the top and contaminating my product. That should not happen, right. Then to reduce that contamination, what I'll have to do is I'll have to increase the reflux. So then what I'm having is unnecessary recirculation in the product column. I don't want that. That's essentially one way of screwing your own self. Okay. So what I will do is I'll say that, look, economic perspective, I want to minimize the loss of C down the bottoms, because C is what earns me money. So let's say I'm going to control X C in the bottoms of the second column to be, let us say, I don't know, some value, maybe 1% or maybe 5%. I would say 5%. Why am I saying 5%? Because anyway D is very small. Okay. Okay, that takes care of that. Because the separation is easy, well, let's see, 1, 2, 3, 4. 4 things are gone. Degrees of freedom is 7, right? Okay, so let's worry about the other degrees of freedom. 99.9% is one spec. 99.9%, that takes care of. Okay, so basically what I am saying is XB in the distillate plus XD, component D in the distillate of column 2. These are the two impurities, right? This should be, yeah.
But column we have only 2 degrees of freedom.
Yeah, so
We are already putting it to a flooding point. If we have increased, like we have fixed the reboiler duty
yeah.
to the maximum.
So if we have fixed the reboiler duty to maximum, then whatever B is leaking down is what is leaking down. See, if reboiler duty is in your hands, you can dictate how much B should leak out. You can adjust the reboiler. Oh, no. You see, reboiler duty here is max.
No, in the second column also.
No. I'm not saying the reboiler duty in the second column is max, because the separation is easy.
We don't want any C to go down, so we will.
Well, so then that is being ensured by that 5%. You can tighten it to 1%. You can even tighten it to 0.1%. Okay.
Yes.
Basically, this is taking care of that. That too much C doesn't leak down the bottoms. That takes care of that.
We can have only 2 options. Like 2.
Yeah. So one constraint is this.
Then it's fine.
Okay.
Yeah.
We are saying that boil up in the first column should be max. Once the boil up is maxed, then what? How much B is leaking out is not in my hands, right? So how much B is going up the distillate is not in my hands. Okay. So this is not in my hands. This is in my hands. My reflux must be adjusted so that what is not in my hands, which is this chap, plus what is in my hand, sum up to 0.1. Yes or no? This is in my hands. I can adjust how much D is leaking up the top by adjusting what? No, by adjusting the reflux. By adjusting the reflux, right? And reflux is not constrained. Yes or no? If the loss term is going to be very small, its magnitude will be comparable to energy consumption. If its magnitude is going to be comparable to energy consumption, I really can't say that they should be max or not.
So we should go for some kind of optimization.
We should go for some kind of optimization. If you say that I don't want to do an optimization, I'll say just choose some reasonable value where you are essentially ensuring too much C doesn't leak down the bottoms. That's the basic idea. Sure, you can do an optimization and come up what this value should be. Maybe your optimizer will say that, look, the kinetics is such that the D loss is too much. Top stream is 70, down bottom stream is, I don't know, top stream is 90 and bottom stream is 10. And then 5% loss is too much. And to reduce that, you keep reducing it. As you reduce it, boil up hits max. Column gets flooded. Maybe that can happen too. But all I am saying is that's very unlikely. When you are trying to maximize production, sure, that will happen. This boil up will also hit max. But at the design, whatever you have designed the process for that throughput, that's not going to happen. Yeah, if you have designed the process for 100 kilomoles per hour throughput, there is sufficient over design in the column, and then if the column is hitting max, then there is something fishy. Chal raha hai recording? Continue. Right? ठीक है कि नहीं? So basic idea is too much C shouldn't leak out, and that we are ensuring by putting that constraint, the last constraint here, this one. Yeah. So we have taken care of 1, 2, 3, 4, 5 things. The fifth one is down there. Yeah. Temperature is unconstrained. Reactor temperature is unconstrained. Yes or no? Why is reactor temperature unconstrained? Because if the temperature is too high, selectivity goes for a toss. If the reactor temperature is too low, conversion goes for a toss. So somewhere in the middle, temperature. So temperature is unconstrained. What is the other thing that is unconstrained? Oh yes. You see, the way this process is, you have to control some composition inside the recycle loop, otherwise either A or B is building up. Yeah. So what are the two unconstrained degrees of freedom that we have left? Reactor temperature and that composition set point. Everything else is constrained. Steady state degrees of freedom for this process is 7. I am going to adjust those 7 specification variables, those 7 degrees of freedom to get desired FA 1, 2 have VSTP at max 2, 3 have reactor volume at max, 4 have only 5% loss of C in the bottom's byproduct stream, 5th sum of the impurities in the product stream to be 0.1%. Then 2 things are left. My question was, what are those 2 things? I am telling you, those 2 things are reactor temperature and some composition that you were controlling to ensure that A or B does not build up in the recycle loop. Does this make sense or no? So I have 7 steady state degrees of freedom. 5 of those steady state degrees of freedom have gotten taken away by economic considerations. What are those economic considerations? FA told to me by management, process so much because this is the market demand. Okay. Maximum reactor level to minimize energy consumption, or rather to maximize yield, because that allows me extra recycle. Extra recycle suppresses the reaction further, side reaction further. Maximum reactor conversion, same thing. Minimizing C loss down the bottoms, makes sense, it's an economic reason. Product purity. So of the 7 things that I had, 4 constraints are active, production is given, 5 things are gone, only 2 things remain in my hands which are unconstrained. The point is, by arguing about constraints, you see that okay, these things need to be controlled tightly. So for example, VSTP max must be controlled tightly. Yeah. So now let's start drawing a control system. By the way, this is at the design. Tomorrow I may get an instruction which says that look, you need to jack up production. Tomorrow I may get an instruction because let us say a war broke out. Okay, and over the next few days or over the next 1 month, this chemical is going to be in great demand. Jack up production, produce as much as you can. So today I am operating at design capacity 100 kilomoles per hour. These constraints are active. 5 degrees of freedom are left. I can still play with those 2 degrees of freedom that are left with me to jack up my production. Yes or no? Yes or no? How would I do that? Now let us say something happens, the price of C goes up too much. Okay, so I would like to produce as much C. Product of C goes up too much. Okay, so I don't have to, the price of C goes up too much because there is some shortage some place, etc., etc. I want to produce as much as I can. When I was processing 100 kilomoles an hour of A, 2 degrees of freedom were left. Okay, now I want to maximize production. That means I want to maximize FA itself. So actually I have got 3 degrees of freedom. FA itself, we don't know what the maximum production is, plus whatever the 2 that was left, composition of A, composition of A and reactor temperature. Now if I am operating this process and I am the operator, and the 2 things that are in my hands excluding FA are what? Reactor temperature and composition. How would I jack up? How would I jack up production? Well, first thing I would say is screw selectivity. I want to maximize, not screw selectivity, some selectivity can go down a little bit. I can produce a little more D, but if I can jack up C, because C is earning me so much more premium, slight loss in selectivity is okay. So what I will do is I will start jacking up the temperature. Okay. Of course, reactor temperature cannot be jacked up infinitely. Either the catalyst will start deactivating or vapor will start getting formed, and that vapor will pressurize the reactor, and then you will reach a pressure limit which cannot be exceeded, and then you will say, oh, you can't jack up the temperature beyond this, right? There will be some constraint on the temperature. Okay, so I will start increasing the temperature. Temperature hits max. That degree of freedom is gone. Okay, then what?
And you will have, if you want to like maximize production, you will have to play with this form some way. You cannot, like in that case, you will just have all this arrangement and you have increased your FA and FP like simultaneously. You will have to do something with this column to make sure this is also economical.
Well, yes and no. I think the answer is no. This column, you see, what is this column doing? This column is essentially doing a CD separation. Economics has changed such that you can allow a little bit of D to go down, but not too much C. Whatever D is going down, that's not earning you money. Okay, maybe you can allow a little more C to go down. Yeah, so leave this column out. Let's play with the reactor. 2 degrees of freedom were there with the reactor, right? What were those 2 degrees of freedom? Huh? Temperature and level was max.
Then it was composition.
Composition. What can I do to the composition? Earlier I was keeping the B composition small, so that side reaction is suppressed. Okay. Now I am saying I can take a hit in the selectivity, because any C I produce makes me tons of money. Even if I produce a little bit more D, it doesn't matter. Okay. So what do? I start jacking up the C composition set point 2. First of all, I maximize the reactor. Now I start increasing the amount of B composition inside the reactor, limiting reactant composition. Let us say earlier it was 5%, now I am jacking it up maybe to 10%. More D gets produced, agreed. However, the difference in the C and the raw material price has increased so much that the extra D production actually is more than compensated for by the extra C production. Yes or no? This didn't make sense. It's 9:50. Maybe we'll have to end.
So
Okay, in the worst case, let us say raw material is free. Okay, then what?
still you have to go for something like maximum purity of C.
Purity is being ensured. Purity is being ensured by the reflux. Okay, so raw material is free. D pay, there is no penalty. This is also not earning me anything. Then basically my objective function is maximize C. Don't worry about how much raw material you are sucking in.
The composition you will have to stick with the same, because the composition ensures maximum conversion, even though we don't need to
no composition, no,
selectivity.
I don't care about selectivity anymore.
Yes, you don't, but if you are playing with the composition, you are not actually producing more, because
no, of course you are producing more.
Your production is fixed by the input.
No.
Feeds.
100. See, I think it's overall material balance. I think you're getting it not right. No, selectivity means, okay, at 100, let us say selectivity was 95%. I am putting in 100 moles of A and I am getting out 95 moles of C and maybe 2.5 moles of D. I go to 150. In the same ratio, what should C be? Or 200 kar lo yaar, 200 kar lo, simpler.
190.
190, and this should be 5. What I will tell you is selectivity has taken a hit. It's not 190, now it's 180, and D has gone up to whatever the hell.
So if you increase the
just a second.
Okay.
So now this 190 or 180 is making me money, lot of money. D, I am not being charged a penalty. A and B are cheap, so cheap that let us say I can call it 0, right? Does it? So the hit in selectivity makes sense or no? It makes sense. That's what I am saying. Whether you can take a hit in selectivity or not is basically determined by C minus A and B price. If that price differential has gone up sufficiently because there was a war, because whatever the hell, there is some legislation that came that basically said that product cannot be used, now this is the only alternative. Others will catch up, but it will take 1 year to catch. You are the only producer of that product in the market. एक साल के लिए आपकी चांदी है, बनाओ जितना बनाना है. Who cares कितना डी बन रहा है, as long as it is small. Do you see what I am saying? Yes or no? So now the instruction from above that has come to me is jack up production, maximize जितना बना सकते हो बनाओ. That's what has come to me. How would I do that?
Sir, if you increase the composition of B, in the end you are gonna lose up on C only.
No, that's not true.
Because in the reactor, C is going to get consumed in reaction with B. So in a way, you are losing C.
Sure, but as far as the over, if that is whatever D gets consumed, that much extra B I have to put.
No, but then
That's
C,
A.
you're
अरे यार,
losing
okay,
with C.
just a sec. A plus B goes to C. C plus B goes to D. This is what we have, right? Whatever D gets produced, because C is getting consumed to produce D. Whatever D I am producing, that requires 2 moles of B, because C is already consuming 1 mole of B, and 1 mole of A. So any mole of D is actually 1 plus 1 mole of A and 2 moles of B. Yes or no? That much extra A and B I will have to put in. Yeah. All I am saying is that since D is reasonably small compared to C, 95% का 92% हो गया, but nevertheless largely the production is 90% or more towards C. That doesn't hit me economically. The economical benefit of producing more C at the expense of producing slightly more D outweighs whatever it is that you are saying. Do you see what I am saying? So therefore I will say, okay, selectivity loss can be taken from 95%, the selectivity has gone down maybe to 92%, or from 98% it has gone down to 95%. Economic scenario is such that I want to produce as much C because that is making lots of bucks for me. Does this make sense or no? That's what has to be done. Time has run out, so shit.